Okay, so I've got a whole bunch of screens open here that, right? One of them is the Natural Language Decathlon and another one is the schedule.
Yeah, I can see both of those.
Okay,
yes.
great. Yeah, one of the things that, there's two things I want with Zoom. I wish they would fix it. One is I want to see what I'm sharing. I want, you know, the person who's sharing stuff should be able to see exactly what is being shared so they can verify that everyone's seeing what they think. And the other thing is, I wish that all of the Zoom windows you'd have the option to dock them all together so that you can, you know, so that you can find everything when you need it. But anyway, hopefully they'll do that at some point. Okay, so let's look first at the schedule. We are today on doing, well, actually I've got the dates wrong, but today we're doing the multitask learning. Next week we'll do the constituency lecture number 18, constituency parsing and tree RNNs. The following week, Dion will give us bias and AI. And then the last one, 20, the future of NLP and deep learning is up for grabs. Anyone that wants to can do that, can take that. So I'll just put open here. And I guess I should fix the dates since we're a little bit behind. Okay. Okay. So let's see. So today we're going to do this lecture number 17, which is a guest lecture by Richard Socher, who is one of the stars at Stanford, one of the NLP stars at Stanford. He has, let's see, I want to find. Sorry, I'm scrambling around here to find what I had. This is not it. This is not it. Oh, okay. Yes. Can everybody see this decaNLP page?
Yeah.
Okay.
Yep.
Yeah. So this is the page that they wrote that describes this code, code that they call decaNLP, which is a combined. They're solving simultaneously 10 different important tasks in NLP, and they sort of wrap them all up in a question answering format. So they have these 10 tasks that they all make to look like question answering tasks, and they're trying to, and they have this super complicated code that solves them all at the same time. And let's see, so this is a leaderboard, and I had expected when I went here to see more recent contributions. So I don't know what the deal is. This is 2018. Perhaps no one's followed up on it, or maybe some better models of, I don't know what the future development here is. Let's see. Oh, Yuri knows something about this. Yuri, do you want to say something about it, since you guys have already discussed it in NLP embedding?
Yeah, sorry. No, I thought it would be interesting to share. I think parse is not in this meeting, but in a sense, this is like an interesting technique that's similar to both transfer learning and to multitask learning. So they combine question answering and similarity problems, but they use it so they can, the reason they use two tasks, because one of them allows them to bring specific terminology, like medical terminology in this case. So that was like a interesting application of basically same. In a sense, it's fine. It's a transfer learning, not so much multitask learning, but it's like a good case of why it should be done.
So are you referring to a subsequent paper, a different paper?
Oh, this is the paper we discussed it like 2 days ago. On this is the paper on like basically medical network, and their goal was to build question answering system, but they use similarity problem to basically train their network, because they didn't have enough. Yeah.
So do you mind posting that on the Slack so that?
Yeah, that's what I did. I posted it.
Oh, great. Oh, okay, super. Okay, so yeah, back to this. So when I look at this, I'm questioning why is it why hasn't anything been done since 2018? And so I wonder if people have come up with more sophisticated ways to do the same thing or whatever. Anyway, that's worth looking into. What's the evolution? What's the follow-up of this thing? Is there something better now or what? Anyway, let's go to the slides. Let's see. So I should be sharing in a minute or so. It takes a little while because I have too many documents, PDF documents open. You should see the first page of the slides now.
Yeah.
Okay.
Yep.
Good. Okay, so let's move down. Okay, so this is work. I guess Richard Socher is, at the time, was the chief scientist at Salesforce. I'm not sure if he still is, but this work was done with a bunch of people at Salesforce Research. Let's see. Okay, so this is the introductory thing, machine learning with feature engineering. That's the old way of doing NLP. Deep learning for feature learning. I think that's still, well, I think that's how we started in this class. And then we did deep architecture for single tasks, some of the things we've done previously, and now this. Let's see. So he first talks about limits of single task learning. And this is an interesting conclusion that he came to from a lot of experience. I think he says that somewhere in here, he says that if you have a classification task, for deep learning to be successful, that is to get something like 80% accuracy or something like that, you need to have 1,000 times as many examples, 1,000 times the number of classes, and 1,000 examples for each class, right? That's what he says. So a good example is ImageNet. You have 1,000 classes and you have 1 million, roughly, your data set is 1 million examples. So that's an example of this rule of thumb. But this is kind of a nice thing to keep in mind, that for deep learning, you need to have, for deep learning classification task, you need 1,000 examples for each class as a rule of thumb in order for it to be successful. And I hadn't come across that before. It's a good heuristic. Let's see, models. Okay, so I guess the overview of this whole thing, and I'm just struggling through this with everybody else. I'm not an expert on this, but the overview of this whole thing is this new approach where instead of training on a single task, you train simultaneously on a whole number of tasks, and then your model that's trained that way can perform well. The idea is that a model that's trained that way, that it's good at all these different tasks, will perform really well out of the box on a new task. So you take this pre-trained model and you apply it to a new task, and then sometimes, a lot of times, you can get really good results out of the box. And if not, you can then fine tune, starting with these weights, you can fine tune for the task that you want. So this kind of multitask trained model is a good starting point for single tasks that you might want to do. And that was the whole idea. And I think he also calls this zero-shot learning, where you, well, I'm not sure, I'm not sure what the distinction between, I'm not sure exactly what the definition of zero-shot learning is, but I think it means, and someone can jump in if I'm wrong, I think it means being able to generalize to a new task without training. In other words, you give it some new task and it all of a sudden does well without fine tuning. Does anyone have a different idea of what zero-shot learning might mean? Okay, let's see.
I think it's like the way I saw it before. It's when you train network on like one set of labels, and you are able to like basically make predictions on labels that you haven't seen before.
Oh, okay.
Like you're trained on like cats and dogs, and you can predict giraffes. That's one way of doing zero-shot learning.
Yeah, Hugging Face recently added a new pipeline. They call it zero-shot classification pipeline. And what it does, I don't know if you've seen that. What it does, you can provide like a list of labels and a context, and it uses like this MNLI style task to choose which of the labels matches best to the context, and does classification in that way. So yeah, that's I think that's coherent with what Yuri just said.
So what's MNLI, you said?
That's when you have like some statement and some context, and a task is to decide whether this statement is like they have, I think they have 3 labels: entailment, neutral, and contradiction. So the model has to decide whether this statement contradicts, or it's neutral, or it's reinforces this, is reinforced by the context.
Okay, so this is called, okay, so entailment means that the statement follows from the context, and
yeah, right.
Okay, and neutral means that the statement doesn't contradict, or neither reinforces nor contradicts the statement.
Yeah.
And that, sorry, the context. And contradiction means that the statement contradicts the okay,
yeah,
so it's
I think they I don't remember how exactly they are called. Like maybe that's premise and context, but yeah, the like general idea is right.
Yeah, so I'm thinking of context as some input statement, and then the second statement is for comparison with that context. The second statement is given as a comparison with that context, and then the result tells you, or the output tells you, whether the second statement agrees with the first, neither agrees nor disagrees, that's neutral, and then the third class is that it contradicts the first statement. Is that your understanding?
Yeah, that's okay. How it works.
Okay, and so what's the relationship of this? Okay, so first of all, what does MNLI stand for? Do you know what it stands for?
Natural language inference, I think, okay. And probably like
multitask,
something. I don't remember what M is for.
Thank you. Okay, and so how is this related to zero-shot learning? Because you're saying that Hugging Face has this. It's called zero-shot learning in Hugging Face.
Yeah. I'll probably link this description, but in general, it it decides like we have this score for entailment for each of the possible labels, and then what model does, it compares, like it extracts this entailment scores for each of labels you provided, and then it does softmax over those entailment scores and treats it as a classification label.
So the entailment score is whether it agrees, is neutral, or disagrees with the original statement. Is that?
Yeah, and like the idea is this entailment score will correspond to how relevant each of the provided labels is to this context, and then like it treats this relevance as label for classification.
Huh. So an entailment score for each label is treated as a relevance, or entailment score for each label is treated as a relevance score, and then you take a softmax over all of those.
Yeah, to choose
then,
one, or you can do softmax with entailment versus contradiction and use it as multi-label classification labels.
I see. Well, this is interesting.
I think I'll share a link to this post about, and it will be clear when you check it out.
Thank you. That's great.
Joseph, there are a couple of links I posted in chat that kind of talk about zero-shot learning, especially with reference to NLP.
Do you want to say anything about any of them?
Actually, I'm just going through them. So, but it defines what zero-shot learning in NLP means, and it seems to have, like, depending on context, different uses. But basically, what you said is the concept that you use a trained model to do tasks that it was not trained on, or data that it was not trained on, as per the first log. But there seem to be multiples of definition.
Thank you so much for that. So we'll have a look at all of that later on. Okay, so yeah, so back to the slide. Yeah, so that's the idea, that we want to get past the limits of single task learning by learning on multiple tasks at the same time. That's the sort of the overview of this thing. Let's see. I'm trying to find the page down key. Let's see. There we go. Okay, we already know that pre-training and pre-training works well from image tasks, and I guess ImageNet plus CNN, huge success. Classification was the blocking task in Vision, and once they broke that task, once they broke through, then Vision was basically Vision was considered to be like a solved problem in machine learning. So now that same kind of revolution is happening in NLP. By the way, these colorful drawings here are colorful slides here. I think they're from this Distill article on I forget what it's called, but it's from Distill, the website Distill. I'll post it, and it has to do with activation maps. Very beautiful graphics showing what your different convolution layers are sensitive to, the kind of things that trigger, the kind of things that turn them on. So yeah, that's really an interesting paper. I'll post that. Let's see. So NLP, we know we start with the encoded word vectors, word2vec. There's glove. There's cove. I forgot what cove is, and then Elmo and Bert. He starts with, in his model, the model that's being discussed in this paper, he starts with glove embeddings for simplicity, I guess. And I guess they moved then to cove. They got eventually got a better result with cove, but I'm not sure if they tried Elmo and Bert word embeddings.
He's one of the original authors of glove too, Joseph.
Right, him and the fellow who teaches this class.
Manning.
Yeah, Chris Manning. Yep. Okay, so he says no single blocking task. Okay, so in classification, so in Vision we had classification was a blocking task, but in natural language there's a lot of, it's really, I guess in Vision problems you have classification and you have object detection. Those are the main kind of tasks in Vision, right? Any others that come to mind? Well, object detection and
semantic segmentation too.
Right, semantic segmentation, where you label all the pixels, where you label every pixel from multiple classes, right? So in that sense, Vision, the scope of Vision problems is not as complex as the scope of language problems. And so he says there's no single blocking task in natural language right now. Let's see, where do we go from here? Why has weight model sharing not happened as much in NLP? So at this point in 2018, weight and model sharing has not happened as much. I think since then it has, especially since Jeremy and the fellow that worked with him, I can't remember his name, they made this breakthrough with, what was it called? Let's see. I forget the name of the model. ULM fit, that's right, ULM fit, yeah. So that breakthrough, I think, I'm not sure if that had happened yet when this class was going on, but so.
Yeah, he refers to it, he had referred to ULM in an earlier lecture, right? So yes.
Oh, okay, right. So they're right in the middle of that revolution right now at the time they're making this class. Let's see, NLP requires many types of reasoning, blah, 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 logistic. Yeah, there's a lot of different, it's a multi-dimensional, I mean, the scope, the space of NLP tasks is pretty huge. Requires short and long-term memory. That makes sense because you need to refer to different elements within the same sentence. You want to have the relationships among different elements in the same sentence, but you also want to be able to have like a whole book, you know, a whole corpus, maybe a book length set of text, and then you want to keep relationships among sentences in the early part of that book and sentences in the later part of that book. I think that's the ultimate long-term memory task, and there may be even longer-term memory tasks. I'm not sure where they are on that right now. Like, does anybody have a feeling for that? Where with transformers and BERT, how long a text can be and still keep associations among all of its elements? Does anybody have a feeling for how long that is? Is it 500 words? Is it 1,000 words? Is it 1,000,000 words?
So I know there is a long former which supports, I think, 4,000 tokens, and BERT is 500. There is a reformer model, which I think since it was released, it didn't gain any much popularity, but it is able to work on like 64,000 tokens.
Wow.
I think it's I never saw it used really like a backend for something.
I see. So 64,000 is a lot, but it's still not as long as a book. Yeah, interesting.
Yeah, and there is this Transformer XL and similar models which do it like they keep this memory like a state of RNN. You know, they don't propagate gradients beyond some fixed sequence length, but they use like this long-term memory which they can write and read from.
So is that like an LSTM, or is it something more sophisticated, or?
Its architecture is like transformer based, but it's stateful transformer, I would call it.
Stateful transformer. Okay.
Yeah, Transformer XL is the most popular, I think, and it was something like some later model. I can share a link to the paper.
That's great. That's very helpful. Yeah, so I guess 64,000 tokens is reformer, but maybe that's a scientific paper or something, an article, but not a book. But that's still, yeah, that's still a lot. But I guess the main you're saying reformer never really took off, so maybe it wasn't very good at
it's
that?
fairly recent, but according to the latest like test, its performance like not really super cool.
So you seem to be up on all this stuff. What is the sort of the latest evolution of transformers that people are starting to use now? Is it just Hugging Face BERT, or?
Excuse me, can you repeat the question?
I'm sorry. So Performer was advertised. I remember seeing the abstract for the paper. It was advertised as, you know, the next evolution over transformers. But you're saying that that its performance isn't that great. So I guess the question is, what is the latest evolution of the transformer model? What are people moving to now?
Well, I think, for example, there is a Performer paper. You know, I was referring to Reformer, and yes, there is Performer, which is different, and it works good, I think, and I think it's not presented at the conference yet. So I'm not sure, but that's like an active area of research. So, and there are a lot of papers coming out, like a lot of variation. I can share a link with to some comparison paper of this architecture. It might be useful too.
Thanks so much. This is great. Are you going to be going to the NeurIPS conference?
Oh, no, I'm familiar with this stuff mostly because I'm participating in this reproducibility challenge by Papers with Code, and we are trying to reproduce this Reformer results.
Oh, that's fantastic. I had looked at that, but didn't have time to get involved in it, but that's really interesting. So you're trying to actually reproduce the code for Performer.
For Reformer.
Oh, Reformer. Okay.
Yeah.
That's fantastic. Well, you should keep us posted on that, you know, on Slack, and let us know how you're doing and everything. That's really exciting.
Yeah, sure. I share some results when we have it. It's like a work in progress.
Are you working with the other NLP groups? I mean, the NLP embeddings or NLP, you know, the other 2 or 3 groups that are in TWIML on NLP?
I'm participating in a paper reading group, which is on Thursday. But we didn't have meetings. This didn't have meeting last week, and we read T5 paper. That's another multitask.
Yeah, I remember that
paper. You know,
is T5
so it's really interesting also?
Yeah, is T5 after this paper, the one that we're studying now, or is it before?
I'm not sure. It's T5 is 2019.
2019. Okay, so it is after this one. Okay, cool. Okay, thanks so much. That's really valuable input. Let's see. So let's go on. Single unsupervised. So he's basically making a case for why we need to have multiple tasks. And he points out that that NLP has had been at that point, and maybe still is, divided into a whole number of tasks that different communities are focused on. And then each community is chasing after the benchmarks, you know, improving their performance bit by bit. But he wanted to sort of unify something. He wanted to sort of unify, make a model that unifies all these tasks. So that's what he set out to do. Let's see, multitask learning is a blocker for general NLP systems. And I guess this paper maybe breaks that. So unified models can decide how to transfer knowledge, domain adaptation, weight sharing, transfer, and zero-shot learning. So that's what he's after. That's what he's trying to build, a model that can be used to to transfer that sort of the expertise of models that are good at many different tasks and combine them into one model, so that then you can show it a new task and it will do pretty well right out of the box, and then you can continue to fine tune it. So here's the thing: more easily adapt to new tasks. That's what I just said, to make deploying to production simpler. I'm not sure how that works. Lower the bar for more people to solve new tasks. Yeah, I guess if you have a pre-built model with pre-trained model, then you can share it out with everyone. Then they don't have to spend all of the compute time to train their model. And yeah, it does sort of democratize NLP. so that more people can get involved in it, because they can do this on their laptop. Okay, why is a blocker, blah, blah, blah. How to express many sequence tagging. So I guess these are the features that he wants to have. He wants to be able to have named entity recognition, sentiment, dialogue state tracking, sentiment classification. I'm not sure what dialogue state tracking is. We know something about seek to seek, that's the machine translation. Summarization and question answering. Remember, that is where you map an input with some number of tokens, you know, say M tokens, to an output with a different, potentially different number of tokens. And that's typical when you translate something from, say, German to English. The translation won't necessarily have the same number of tokens as the question had. The same goes for summarization. You give it, you know, you give it some paragraph or something, and you ask for a summary of the paragraph. And so the input and output number of tokens is different. Same thing with question answering. So that's the seek to seek. So he wants to combine somehow all of these tasks, seek to seek, classification, and sequence tagging. And I understand named entity recognition. That's where you can classify something as a company or a country or a city or whatever. I'm not sure what aspect specific sentiment is. Okay, so 3 equivalent supertasks of NLP. These are the ones I guess he wants to combine: language modeling, question answering, and dialogue. And this is sort of a map of this is sort of indicating that how that going up they get more complex. I think that's what he means. I'm not sure. Let's see. Let's see. Do I have this? Okay. Okay. So then that's what this is what he's developing. The Natural Language Decathlon, decaNLP. That's this paper. So he's got 10 different tasks. And this sort of summarizes them. There's 5 tasks in this column and 5 tasks in this column. And these are examples of each of the tasks. So this one we can recognize: translation, summarize. We understand that. We've seen it. Entailment. That's what Arto just, I think Yuri or Arto, I'm not sure which one. So one of you told us about entailment. I think it was Yuri, right?
Yeah, I was talking about it. Yeah, that's
right.
Task exactly.
That's right. And then sentiment, I guess positive or negative classification. This one I don't understand. What has something experienced? I don't understand why that's an important question. I mean, I see that this is an example, but I'm not sure why. This is a question answering task, I guess. So you give it a paragraph and you ask who is the illustrator, and it figures it out. This is something I don't understand. Change in dialogue state, I don't understand that. Context, are there any Eritrean restaurants in town? Food, so you, oh, okay, so you look at a question and you somehow classify it as a type of question and give the answer. I'm not sure what that, but that's apparently what they mean by dialogue state. This is an interesting one: translation from English to SQL. So you give it a query in an English, you know, in English. You know, you say, I'm going to give you a table with these column names. Tell me what the notes are for South Australia, and then it translates that into a SQL statement. That's kind of interesting, an interesting task. Who had given help? So this is, I guess these are all examples of tasks that he wants to sort of encompass in this model, in this decaNLP model. And then there's more, let's see, I guess, and this is the more specific naming out of the 10 different kinds, the 10 different tasks, right? So question answering, we are familiar with that. Machine translation, summarization, natural language inference. I'll come back to that. Sentiment classification, we know about that. You know, Amazon reviews or whatever. Common sense reasoning, semantic parsing. Not sure I could define that. Dialogue. So that's, I guess that's where you, the input or context is some statement, and then you have to, and then somebody has to come up with another statement that follows from it or is some way related to it. Relation extraction, that's kind of like named entity recognition, I think. Semantic role labeling, I'm not sure what that is. Can anyone comment on any of these? I think most of them we can see that we understand because we've encountered them in our in this class before, but there are some of them that look new. You know, like I think what Yuri was telling us about is natural language inference, the entailment task, I think. Common sense reasoning is kind of very broad. I'm not sure how I could define that. Anybody have any comments on any of these tasks? Can add to our understanding. For example, semantic parsing. Is that just, no, that's, no, I don't know what semantic parsing is. Semantic means that word is related to meaning. And parsing is somehow dividing up a statement. So I don't know what semantic parsing is. Anybody have a clue? What about natural language inference? Can someone give sort of a broad definition of that? Okay, well, let's leave those up in the air then. Okay, so this is what he sort of calls the work that he's doing, he calls it meta-supervised learning. And in the sense that you're trying to solve all these tasks at the same time, but nobody's telling you which one is the main task. You have to figure, the code that he's writing or the system that he's developing has to figure out what the important, so if you give it a problem, the system has to figure out the relative importance among these 10 tasks, so in some sense, to figure out what kind of a question it is. So, yeah, so see, so X to Y, X is a context or the input statement, Y is the answer. And in some way, he has to figure out which task you need to solve to get to the answer among all of these tasks, or somehow figure out how much of each of these tasks is needed. You know, what are the weights or something? What are the how much you know, given a task, given a question, you have to figure out like how much should I lean on machine translation for the answer? How much should I lean on summarization? How much should I lean on relation extraction? It sort of has to figure out sort of how much effort to put into each of these tasks. Okay, so that's sort of my understanding of that slide. And so here's again the specifications that he's trying to develop a system to these specifications. No task-specific modules or parameters, because we assume that the task is not available. So that's what I was saying before. You don't know which kind. You know that you can get the answer by considering all these 10 kinds of tasks, but you don't know which kind of task you're dealing with when you're given an input. Must be able to adjust internally to perform disparate tasks. So you have to sort of figure out how to do all these 10 tasks in your code. Leave open the possibility of zero-shot inference for unseen tasks. So this gets back to the zero-shot inference definition. It seems like zero-shot inference is some kind of a holy grail, like you want to be able to generalize to an unseen task. And I don't know of a good example of zero-shot inference right now. So that's something that we can explore the references that Srinivas has provided in the Slack group. All right. Okay, so here's the the architecture that he came up with, and it's quite complex looking. But the overview: you start with a context, you ask a question, you generate the answer one at a time by somehow a combination of these three things: pointing to a context, pointing to a question, or choosing a word from an external vocabulary, and you somehow combine all of these things. He talks about pointer switches as if we already know about them, and I don't recall encountering these things in any of the previous lectures. So I'm not clear on what a pointer switch is. But I think it's some way of combining different inputs, like, and I think they explicitly do it by means of let's see. No, I'm not sure. Let's come back to this. Okay. Page down. So this is the he'll come back and look at this architecture a little bit later. So yeah, here it is right now. So we can just sort of consider what it looks like. So you have a question and a context. The context is some text that that you get to look at. I think that's what it means. So you give it a paragraph of text and then you ask it a question. And then, so there's these layers, initial encoding, co-attention, transformer layer, and then answer. So let's look at these one at a time and see if we can make our way through it. The first layer is easy. It's just the initial encoding, and it's done with glove. I think he just has a fixed encoding for each of these things. Then that goes into, I'm not sure. So let's see. I'm not sure what this is. These might be, I'm not sure what these two things are, but I think they're bi-LSTMs. That's what I think they are. And then, so the encoding goes into that bi-LSTM, but it also goes into the context bi-LSTM, and the context also goes into the context encoding goes into the question bi-LSTM. And then another interesting connection is that the encoding is directly connected to this co-attention layer, and the context is, sorry, the question encoding is directly connected to the co-attention layer for the context, and the encoding for the context is directly connected to the co-attention layer for the question. So there's this cross connection going on. And then it's even more complicated because there are two of these co-attention layers, and there's like a skip connection, but it's complicated because the skip connection goes from the context output to the input of the question co-attention layer. See, and then it's symmetric. The question output in this side, there's a skip connection between it and the co-attention for the context. So there's this sort of symmetry, but it's kind of pretty complex. Let's see. So let's see. So this is called the co-attention layer, the one we just worked through, without really understanding too much of what's going on, just sort of the internal structure of it. And then he has a transformer layer times 2. So I imagine that this thing, that these elements are duplicated. In other words, you do it once and then you do it again. These are bi-LSTMs, I believe, these green things. Then there's a multi-head attention that goes into a feed-forward network. That's a fully connected network. And then to a final encoding. So there's there's a BILSTM, there's BILSTMs sandwiching the transformer layers. And I'm not sure why he had to do that, but yeah.
Maybe those are not by LSTMs, those are just those arrows which go both direction, are just to emphasize the fact that these are bidirectional encodings, like in BERT, you know.
But I think he did mention that he had to sandwich the transformer layer with BILSTM before and a BILSTM after. I think he mentioned that.
That's interesting.
In the lecture. Yeah, so it's complex, and then that's not even the most complex part. Then there's an output from the question side and an output from the context side, and then that goes into a question pointer, and let's see, and that's what I don't understand. He talks about pointers, and then the output from the context side goes to a context pointer. But there's a skip connection on the context side, apparently. Yeah, this is pretty complicated. So then, so there's three outputs. I guess if you're trying to look at it at a high level view, there's three outputs. There's a question, there's a context, there's an answer, and then these things somehow get combined by softmax or something. So sorry, I can't be more specific because I'm trying to understand it myself. My answer. So this looks like another multi-head attention layer, a transformer layer. Although, let's see. Yeah. I wonder, is this? So this transformer layer is, or this attention, so this transformer layer is multiplied by 2. This one is just a single one, and it doesn't have these BILSTMs on its input and output. I'm not sure what this is, this yellow thing. But yeah, sorry, I can't be more helpful about decoding what all this means. So that's the architecture. Before we move on, does anyone have any edifying comments or questions about it that we could think about?
Joseph, my question is it decaNLP, is it state of the art? Because I can see the link shared is like, there isn't any state of the art. I mean, the dates of some ledger body is somehow outdated. I'm not sure if this is updated work.
Yeah, I think that's a really good question. That was my first, that's the first thing I noticed when I went to his decaNLP website, is that it hasn't been updated since, the leaderboard hasn't been updated since 2018. So I would think that it hasn't really, it hasn't caught on. There must be something better for this, maybe the T5 that Arto was talking about might be the.
Yeah, so this one might not actually.
Sorry? Shamsuddin?
Okay, so my question is like, so this decaNLP might have not actually have a success toward this multi-question answering network.
Yeah, I think you might be right. I mean, he did have some success, as he talks about towards the end, but maybe maybe something else, as you suggested, maybe something else has superseded it as more important now. And excuse me, and I know that from what Arto said, another multitask learning system is the T5 architecture, and maybe that is what superseded this thing.
Yeah, about T5. They had compared like multitask learning with like multitask pre-training followed by fine-tuning, and fine-tuning was still like considerably better than multitask learning. But I played a bit with models they have in Hugging Face, and it indeed can do multiple tasks. Like you don't need to load separate weights. You use just one model, and it has good performance on all the tasks at the same time.
So Arto, question for you is, what does Hugging Face use for its multitask learning architecture?
Yeah, that's a good question. That's a good question.
I'm not sure about what do you mean by multitask learning architecture? I'm not sure Hugging Face, I don't know exactly, but I'm not sure Hugging Face has like a single multitask multitask pre-training framework. It's not like that popular in practice. Like Hugging Face is more practical, and this is, I think, multitask learning is still closer to research. But maybe I don't know. Maybe someone else knows better. And also, another model to mention in this context is BART model. It's a model by Facebook, and I think it has some fair amount of state-of-the-art high places in many sequence-to-sequence tasks.
What's the name of this model?
BART.
How do you spell
BART, but with A.
Oh, BART, like Bart Simpson.
Right.
Okay. So that's their multitask model? Facebook?
Well, I'm not really familiar with the way they trained it. I just know it's used. Has uses on most of the tasks the same as T5. But I don't know any details on that.
I see. But Hugging Face does implement T5, right?
Yeah, right. You can take it, and they have 5 variants of T5 pre-trained, and you can use it. And about T5, it formulates all tasks like sequence-to-sequence task. So classification tasks are reformulated in like a sequence-to-sequence task. So it just generates an answer, even if the label is like classification label. It just generates some token, and those tokens are treated like output.
So here, this model we're looking at, this decaNLP, formulates everything as a question, I think, formulates all 10 tasks as questions. But you're saying that this T5 formulates all 5 of its tasks, of the component tasks, as seek-to-seek tasks. Is that?
Yeah, T5 is comparatively simpler than this one in terms of architecture. It's like very similar to standard transformer, and the thing about it is how they formulated those tasks.
Yeah, so maybe if he were teaching this class last year, he would have maybe included T5 instead of this one. I don't know. Yeah. So let's move on from this diagram. Page down. Multitask question. So, okay. I guess he's going through it piece by piece now. So this is the question context, initial encoding, shared by LSTM with skip connection. So I guess these are the by LSTMs. And then attention summations from one sequence to the other and back again with skip connections. That's what we saw here. So there's attention, there is, and it goes from across tasks, across these two tasks, and then it has a skip. In each case, it has a skip connection with the second layer. So there's two layers here, and the second layer is connected to the first layer, but then there's also a skip connection that connects with this component of the other layer. So you can see there's one skip connection connects this blue rectangle to this red attention layer. And then another skip connection connects this blue object here. I'm not sure what this is actually, to the opposite second attention layer. So that's what he's saying here. I'm not sure does anybody have a feeling for what these things are, these two things? So this is a BioSTM. Not sure what this part is here, but these two blue rectangles are. Anyway, so let's move to the next slide. Then he adds the transformer layer that we talked about. Remember, there's it's sandwiched by LSTMs on the input side and the output side. Separate by LSTMs to reduce dimensionality. That's I guess that's the trick, I guess. Maybe these are the two transformer layers, another by LSTM. Separate by LSTMs, that's these things maybe. Then two transformer layers, then another by LSTM. So I guess this thing, it's not this whole thing that's repeated twice, it's just the inner part that's repeated twice, according to what he says here. Just this part, the multi-head attention coupled into the feed-forward network, that's repeated twice. Okay, then autoregressive decoder uses fixed glove and character n-gram embeddings, two transformer layers, an LSTM layer that attend to outputs of the last three layers of the encoder. The last three layers. I don't understand this part, this autoregressive decoder part. I guess that's what, so he's taking us through it piece by piece, adding these layers. But this is the one where I'm kind of lost. Don't understand what it is. This structure looks the same as that structure. Anyway. So there's, I think, so that's, and then this is the next step. Where he's getting this vocabulary distribution, he's getting context pointer and a question pointer. These are the two things that I don't understand. And Socher talks about these like we've seen them before, but having seen all the previous lectures in this course, we haven't seen those before. So maybe he talks about it in his paper. There is a paper, MQAN paper. There is this decaNLP paper that maybe he discusses it. And I actually looked at this paper, and it doesn't look like it would be too much trouble to read. It's what I like about machine learning papers is they've sort of evolved into a format where you get everything in all the important stuff in 10 pages. If you look at these NLP papers, they usually try to deliver the message in 10 pages, and then there could be more pages with results and so on, but the main part that requires work to understand it is in the first 10 pages. Then there's a bunch of results, and then there might or might not be an appendix containing all the impenetrable mathematics that they had to use to get to their results. But usually they're formulated such that if you can read the first 10 pages, you get a good idea of what it's about. And this paper is like that as well.
I haven't read the paper, but isn't, at least from following this discussion, aren't question pointer and context pointer just distributions that are attentional distributions that help you point to different portions of the question or the context, and therefore they are then used as distributional outputs that are, we have yet to see how they get used, but isn't that the thing rather than an entity by itself?
Yeah, you might be right. It does look like that. That maybe the word pointer is something that's confusing, but maybe you're right. Maybe it's just a distribution, because that's what this looks like. And then in the end, they somehow combine these things with some kind of a softmax process to get the final answer.
Yeah, because to me, it seems like they're just attentional distributions of question attention and context attention, and then this external thing he talked about, which is external, and then deciding on, as you said, the combinations of which of those to generate the next word in the response.
Yeah,
how that happens,
may be.
we are there to see.
So like in extractive question answering, we have like this distribution over all tokens, and we choose a most probable span to get an answer. So Srinivas, you're saying that's like that, right?
Yeah, that's what I mean, that it's just a distribution, and then the choice of how the distributions get combined in order to make the decision on the next word is we're yet to see. But so the pointers just seem to be extracted attentional distributions.
Yeah, because they come directly from the outputs of these transformer layers. But then there's this one, and I think this third thing is somehow one of the keys to the success of this thing, because this allows it to perform, or to this allows it to generalize to I guess to words that are outside of both the question and the context. So, you know, in other words, you have a paragraph that is a context, and this is some paragraph that you have to read, and then you have to, and then you have a question, which is also a text, a set of text, and you're supposed to read the context and answer the question. But this allows you to go outside the words that are in both the question and the paragraph that you're trying to analyze. It allows you to go out into your entire vocabulary and understand which words might be related to the answer. So this is probably a key in being able to generalize your question answering process. So let's see. Okay, so here's discussing how the whole thing works. Attention over the context and question influence two switches. I guess that's the question pointer and the context pointer. Gamma, that's gamma here, decides whether to copy or select from an external vocabulary. Copying means just using words from your question. So gamma decides whether to copy or select from an external vocabulary. That's this one. Lambda decides whether to copy from context or question. So lambda is, I guess, some kind of a switch that combines the words, the distributions, as Srinivas said, from the question and context, decides how much of that to mix in, and then gamma decides how much from the external vocabulary to mix in, and then these three things, the question, context, and external vocabulary, get somehow combined to give an answer. So in a high level, we can sort of understand that, and that makes sense. So that's all the sort of the theory part. And now he's sort of summarizes or he goes through some of his results. And so he has these 10 particular tasks that he's trying to solve. For each task, there's an associated data set. One we recognize as squad for question answering. I don't know this. It's some kind of a language translation from English to German. Summarization, CNN, Daily Mail, so you're summarizing news articles. Natural language inference, this is a data set, I'm not familiar with it. Sentiment analysis, I'm not familiar with that one. Not familiar with either of these or this. Wiki SQL, that's the task of converting an English sentence to a SQL statement, to a SQL query. So that's interesting. Pronoun resolution, I'm not familiar with Winograd's schemas, so there's specific tasks, specific data sets, and specific metrics. And they made the decision in each case, the people who are running these sort of tasks have decided on what's the good data set and what's the good metric to use. And he decided not to second guess any of these. He's just going to add up all of the metrics as originally defined. And that's going to be his metric. NF1, normalize word level F1, case insensitive, no punctuation or articles. Rouge, I think we had talked about that, although I'm not remembering much about it right now. EM is exact match. CF1 is corpus level F1. Dialogue state EM. Not sure what that means. Logical form EM. Anyway, in each case, the task has its own metric. And I think the metrics go from 0 to 100 or something. And so all he does is he adds them up to get his metric. Let's see. DECA score, that's the Natural Language Decathlon. DECA score is the sum of task-specific metrics. And so this is what I just said. He just adds them up. People had argued back and forth about how much we should weight this or that, but it just wasn't, you couldn't really come up with a principled, reasoned argument for how you should weight these things together. So he decided that the team decided they're just going to add them up. Okay, so here's the 10 tasks. Here's single task performance, seek to seek, self-attention, co-attention. I don't know what that means. So he has, he's considering each, let's see.
I think it's like ablation in the sense that if you just did that, and then how much does it improve when you do add self-attention, then co-attention, then the pointer thingy. And so I think it's kind of indicating as you build or add pieces to the architecture what your single task perform. That's the way at least I thought to interpret it.
That makes sense. And then, so I guess he says here that S2S is seek to seek. Then you add the self-attention, then you add the co-attention, then you add the question pointer, which I'm not sure that, but that is how you get the MQAN score. That's the MQAN is this is the name of this whole overall task. So, but there's two kinds of scores that he gives. One is somehow when you consider each task separately, and then the other one is when you consider all the tasks together. And he points to a gap between these scores. I think maybe we'll find that later in one of the later slides. I'm not sure what this single task performance versus multitask performance is. I thought that the whole idea of this decaNLP is to give a solve all of the tasks at the same time.
I thought it was actually, yeah, in a single task performance. So like, for instance, in the squad, I thought he would take his big network and train it all in the squad data and then see how it does for each of those things, but just trained purely on squad. Then when you come to the multitask, I thought he'd trained it onto all 10 of the different things and then run the tests, but I could be wrong.
No,
But,
I agree with you, Steve, that's probably what he did is that is the performance of the model when trained on and executed on a single task versus the performance when it is trained on all the tasks and then execute the various individual tasks. You eventually end up in doing it, but your model state is different because you've gone through the training of taking the model through training of all of these in the multitask case.
So, but you can't really, okay. So you can't really train all the tasks on one data set because each task is very specific. They have different data sets. So,
yeah, but you can train the model on, so let's just, to keep things simple, let's collapse the vertical axis, right? So let's just assume we take just we have plus Q pointer. So that's the end model, which has the sequence to sequence plus self-attention plus flow attention. So let's just focus on these two columns, the plus Q pointer one for single task and the plus Q pointer. Then what you do in the first case, in the first case, you just train the model on squad and test it on squad and you get this result. Then you take the model, you train it on the next row and you test it on that and you get 25.5. You train it on this, you take the model, you take that model, which has been trained on this task and test it on the same task. And you do that for for row after row and all the 10 rows. In the next case.
Wait, stop there. That's the part I don't understand because the way this thing is defined is it has to have all 10 tasks in it. So how can you train it on just squad? You have to have all the tasks in it.
It doesn't have to have all of them because it's like a general model where like it's purely you're asking a question and getting an answer. It doesn't matter which task you're running. So you can train it on all 10 things, and because of the fact you're just asking a question and getting an answer, you can like use it on any of them. But yeah, like as Srinivas says, I think so on the left-hand side, the single task performance set of results, I think he's just trained it purely on squad and then evaluated it there just purely on squad. And then in the second row, he's done for whatever that is, the IWSLT. Whereas in the multitask performance, I think he's trained the whole thing on all 10 and then evaluated the model. And he can do that because of the fact it is a general model, that because of the fact he doesn't have to sort of change the head on the model, he can just ask a question and get an answer out. And so he is capable of training it for all 10 things and then evaluating.
Okay, so that begins to make some sense. So so trained only on squad, here's the result. And if you compare this column to this column, you notice that in most cases, although not all cases,
his line's actually in the wrong place, though, isn't it?
Yeah.
So the line should be the line should be one column to the left.
It should be here. Yeah, it should be here.
Yep.
So this is okay. So this is the final score we want to compare. Okay, so we want to compare this score to this score. And in most cases, that's a good point, Steve. Thank you. In most cases, the single task score is better than. In fact, in all cases, well, this case it's not. But they're almost the same. But and in this case, the multitask score is better. But all the other cases, the single task score is better. So he wants to improve the model so he calls that the gap, the gap between the single task performance, which is usually better than the multitask performance. And so he calls this the gap, the difference between these two, and he averages. So the average difference between these two columns, the Q pointer column for single task and Q pointer column for the multiple task, that difference is called the gap. He calls the average of that distance is called the gap. And then he says, okay, what we'd like to do now is improve the model to make the gap disappear. And so he actually does that by means of some methods that, one of them is he goes to a cove embedding instead of glove. And I think he talks about that in the following, what he does to get the gap down. Transformer layers yield benefits in single task and multitask learning. So I guess he's pointing to the difference between the earlier score and the later scores. They do improve on both sides, both single task and multiple task learning. So when you add these attention layers, you get better scores. That's one thing he says. Oops, sorry, I didn't want to do that. Moved too far. Page up. Sorry, I'm trying. Can't seem to move up. Yeah, here we go. Okay, this is where we were. So here's his, Transformer layers yield benefits in multitask, in single task and multitask settings. So that's the slide we had just looked at. So these are the conclusions that he made here. QA and SRL have a strong connection. QA, I'm not sure what, QA is question answering. SRL is, I'm not sure, but he's pointing to the idea that these two scores are similar, or that the model is strong in both of these. Let's see, down. The next takeaway is pointing to the question is essential. So QPTR makes a big, well, in some cases it makes a big improvement here to here, here to here. Yeah, so the question pointer part of the model is important, he's saying. Transformer, let's see, the question, transformer. Multitasking helps zero shot. I guess this is a zero shot task. I'm not sure what this task is. It's some kind of question answering, but I'm not sure what ZRE means. That's a problem with a lot of these papers, and it's particularly in this class where they give the summaries of all the different data sets. They don't write it out, so you don't really know what they're talking about unless you go and look at the paper and look it up. But this task is apparently a zero-shot learning task, and the multitasking part does a lot better than the comparing that score with that score. You see that it does almost twice as well. So the multitasking helps a lot in that case. Oops. Where was I? Again, I made the mistake of going all the way back to the end when we're only really on page 35. Let's see. Sorry about all the scrolling. Trying to get back to where we were. Page 35. There's where we are. Okay, so now he talks about the training strategies, and he talks about a fully joint strategy where you're running a single batch through all the tasks. And that's the sort of the schematic. It goes through the tasks, all of the tasks. But then he says that they found that a better strategy was called, he called it anti-curriculum pre-training, where you run the tasks sequentially in decreasing order of difficulty. In other words, you run the hardest tasks, you run the batch through the hardest tasks first. Oh, and then you run it through multiple epochs. You see, let me go back. So let me start. Okay, here's where it starts, anti-curriculum. So I'm gonna just sort of scroll through this, and you see the batch. You're running a batch through task A, then task B, then task A again, then task B again, and those are the harder tasks A and B, and then you run it through the rest of the tasks. Let's see, reddish tasks included in the pre-training phase, and those are the harder ones, I guess. And difficulty, how many iterations to convergence in the single task setting? I'm not sure what that means. Let me see. Yeah, I don't know. Then he says that this improves anti-curriculum pre-training for QA. That's what we just saw, where you run through the harder tasks several times, several epochs of the harder tasks. Sorry, you run a batch through the harder tasks several times, and then through the easier tasks. And he says that anti-curriculum training, as opposed to the joint training, fully joint training, works better. But so looking at these columns, oh, there's the anti-curriculum training, and there's the, I guess this is the score from the fully joint training. I'm seeing it generally better, but not always. But he says the machine translation task was still bad. Which one is machine translation?
Second row.
Second row, okay. There we go, English to Deutsch. Yeah, so anti-curriculum training didn't help with that one. Okay, so closing the gap. So now his more recent research is trying to close that gap we were talking about between when you run the model singly on the individual tasks and average the results and add up the results, versus running the model, training it on all the tasks at the same time. And so he says the score was, with fully joint training, was 563. Let's see, the set. Okay, so this is the full model, the multitask model, and this is the set of single models, and that was better. The set of single models was better by 23. So he's trying to get that, close that gap, to make it smaller and smaller. So he says when he used anti-curriculum training, squad pre-training, I guess squad is one of the hardest tasks, so you run that one first. He said they dropped the gap dropped to 15. Then with Cove, it increased the gap but raised the overall performance. So that's interesting. Then by including more tasks in the first phase of the anti-curriculum pre-training, that is, instead of just squad, you pack in some of the other harder tasks. Remember the red tasks versus the blue tasks. You run through the red tasks first, maybe multiple times, and then you run through the easier tasks, the blue tasks, if you remember that slide. So he says by including more tasks in the first phase, that is, including more in the red tasks, the ones that you put up at the front and run them several times, he could drop the gap to 5 points. And then by oversampling on IWSLT, I'm not sure what he means by that, he dropped the gap to 1 point. So he basically eliminated the gap. Eventually, their work allowed them to eliminate the gap. So now, training individually and adding the resulting scores, you get roughly the same result as when you train the model on all of the tasks at the same time. Okay. Deca score. I'm not sure what this is. So this is the Deca score. Wait, I should be looking at this one, right? 586. Showing the improvement with Cove instead of glove embeddings. Showing anti-curriculum training. Showing using Cove and tuning. So there's 616.8 and there's 618.2, and that's the 1 point gap that he was talking about. Okay, let's see, where MQAN points. So these are the three components of the tasks that of the score the three components of the final part that we looked at. You know, the external vocabulary part, the context part, and the question part. And it's showing the distribution of those things for the for each of these 10 tasks. So looking at these, you see that most of the tasks are dominated by one of them. In fact, every one of the tasks is dominated by one of these things. Let's look at the language translation one. It's dominated by the external vocabulary. Squad is dominated by the context pointer, the words in the the words in the reference text. And I'm not sure how to decode it. I wish they would write these all out. MNLI, SST, I'm not sure. These things are all, these three tasks are dominated by the question, the text in the question, I guess. No confusion over which task the model should perform or which output space to use. So the fact that each of these is dominated by one of the output spaces, I guess this is what he calls the output spaces. I guess he considers that a good thing. I'm not sure what else to make of that. Okay. Pre-training on decaNLP improves final performance. On final performance on what? That's what I don't understand what he means. MQAN, pre-trained, that's this model that we're talking about. Pre-trained on decaNLP outperforms random initialization when adapting to new domains and learning new tasks. So now I'm confused. MQAN and decaNLP, I thought I understood them. I thought they were the same thing. I'm not sure what MQAN stands for. decaNLP is this model with the 10 tasks in it.
Well, I believe decaNLP is referred to the data set which they use, like this combined data set, and MQAN is this model architecture.
Okay. Okay, that makes sense. So this is the model architecture. This is the specific data that it was trained on. And now you can then take this same model and apply it to a new task like a language translation task here, or named entity recognition. So I guess this would be, let's see, left is the training on a new language pair. So you take this pre-trained model and try it on a new language pair. And then the blue, the red here is a random initialization of the weights, and but it's the same model, but with randomly initialized weights. And then blue is where you take the pre-trained weights from decaNLP. And the performance with the pre-trained weights is better. In both cases, both the language translation tasks and the named entity recognition task. Although I would have thought it would be much better, but it's not that much better. But anyway, yeah, I mean, 86.1 or something to 86.3. I mean, so that's the improvement. Okay, so pre-training helps. That's one takeaway. zero-shot domain adaptation of pre-trained MQAN achieves 80% accuracy on Amazon and Yelp. So that's what I thought it meant. Is zero-shot domain adaptation means you take a pre-trained model and you apply it without changing the weights, just taking those weights as is, and you apply it to a new task. In this case, Amazon and Yelp reviews, and you got 80% accuracy right out of the box. I guess that's what it means by zero-shot domain adaptation. But that's pretty impressive, I guess. SNLI, I'm not sure what the SNLI task is. Does anybody remember or have come across that before? Neural language inference. S, I don't know what S means. 87% with fine tuning, a 2-point gain over random initialization. 80. This I don't understand. So this is like taking the pre-trained MQAN right out of the box, and it gets 62%. Oh, okay. And then if you fine tune, you can get up to 87%. But then he says, if you don't use the pre-trained model and just go from scratch, in other words, random initialization, you only get up to 85% accuracy when you fine tune. So that's how I understand this one. So he sort of succeeded, in what he tried to do is to build a model that can do zero-shot learning. Zero-shot classification. Question pointer makes it possible. Question pointer makes it possible to handle alterations of the question, i.e. transforming labels to labels positive to happy, supportive, and negative to sad, unsupportive, without any additional fine tuning. So if you have like a two-way classification problem with plus or minus, like if you're doing like reviews and you have either thumbs up or thumbs down, you can run that out of the box on another two-class problem where the classes mean something else. In this case, happy / supportive and sad / unsupportive, without any additional fine tuning. Enables the model to respond to new tasks without training. So John had a party, but no one came and he was all alone. Is this story sad or happy? And the model says sad. And I'm guessing that the task that was in the pre-training was review classification as positive or negative. And here that without changing it, it understands that in this case, a positive label would mean happy or a negative label means sad, I guess. So you sort of mapped a two-class problem, classification problem, to a different two-class classification problem. Okay, so here's like he's getting to a summary slide, I guess. decaNLP, a benchmark for generalized NLP. Train a single question answering model for multiple NLP tasks. Questions. So that's the sort of the framework here. He considers all of these 10 tasks. He considers them each as a question answering. He addresses each one of these tasks with a question answering model. And this is kind of like what was said earlier about the T5 model, where in that case, all the tasks are seek-to-seek tasks. And so he's shown that this is a framework for tackling more general language understanding, multitask learning, domain adaptation, transfer learning, weight sharing, pre-training, fine-tuning. So we've seen examples of all that, and zero-shot learning. So that's kind of like a summary, or close to a summary. Related work. So then he says, these are a bunch of papers. He says he said actually that they considered 100 papers as the input to their project. They looked at 100 papers, and here's a small subset of them. some of these are collaborators that we recognize from earlier papers that we've looked at in this class. See, I remember this one at least. This one. I don't. There's Chris Manning.
So there are a lot of authors of the Attention is All You Need paper in Kaiser, Vaswani.
Yeah, and Sutzkeber, is that another one of them? Ilya Sutzkeber,
Yeah.
This guy.
Yeah.
Let's see, Manning, Bengio, Collibert, and Weston. I think we've seen papers by Collibert and Weston. I think this was one of the papers earlier that we looked at, or maybe at least these are the authors of some of the papers we looked at earlier. Anyway, this is a bunch of papers that they considered when they built their model. And what's next? Single multitask model TBD. I'm not sure what he means by that. I thought that's what this was. What the MQAN is. Anyway, so that's the summary. And that's all I've got. Are there any other comments? I think that I really appreciate all of the very useful comments that you've made and that you're and the links that you're posting on the Slack for further reference. So yeah. So so next week we'll do number 18, lecture number 18, which is let me just review that quickly. It's constituency parsing and tree RNNs. So that might be interesting. And then I think Dion has confirmed that he's going to do this, or I think it's a she. I think she's confirmed that she's going to do this, but I'm going to make sure. I'll send out a message to her. And then as I should have said at the beginning, anyone who wants to, this one's open. I don't have anyone to do this one yet. The last lecture, Future of NLP and Deep Learning. If anyone wants to take that one, you're welcome to.
So it would be in 2 weeks, right?
Yeah, I've got the dates wrong. I've got to fix it, right? So we're just going to go through the rest of this. We're just going to go through one week for each lecture, right? So here we are today. I have to fix the dates. Next week we'll do this, and then we'll do the following week bias, and the following week future of NLP. So
okay, I would like to try this future of NLP lecture.
Excellent. I will edit that right now. Let's see. Do that. By the way, what's your actual name?
Artashes.
How do you spell it?
Artashes.
Artashes. Like that? Oops, sorry.
E. The last vowel is E.
Artashes, like that?
No. I'll bring in the chat.
Okay. Anyway, very appreciative of your doing that. That's terrific. Chat. Oh, sorry. Chat. Artashes. Okay, got it. Okay, let me just fix that. Great. Oops, I just messed that up. Anyway, yep, there it is. Okay, appreciate that. Thank you.